So let's start. So our next talk is by Swen, who you see here, and it's parameterized verification of systems with precise 0-1 counter abstraction. Take it away.
Yes, thank you. Good evening, Denver. This is joint work with Paul and with Chana Weil-Kennedy. Paul is my PhD student who was supposed to present, but sadly he had a health issue and couldn't join you in Denver. So instead, I will do my best to present his slides. As a very high-level idea of what the talk is about, it's about parameterized verification, which you can think about as verification of systems, component-based systems, regardless of the number of components that run in parallel. And well, 0-1 counter abstraction is our main proof technique, let's say. And what the title doesn't tell you is that it's really the heart of a framework that allows us to capture many of the existing results for systems that have decidable parameterized verification, and also a couple of new systems. Okay, so motivation-wise, of course, we're in an age where even a single processor has multiple cores, dozens of cores actually, or hundreds of cores. And applications might run on multiple processors, so hundreds of processes of any given application might execute concurrently, and then ensuring correctness, so ensuring that certain things will happen or other things will not happen, is very difficult. And this is where we want to use parameterized verification. Taking a step back, what is like the optimal setting for verification is if we have a finite state system represented here with a finite number of states, and we, for example, want to check some specification which might be just reachability of a state or some more complex property. We can give it to we can devise a model checker, and we can give it to the model checker, which can automatically decide whether the specification holds or not, whether the state is reachable or not. This is, let's say, easy for a finite state system, but in our setting, we want to have such a process, and then we want to execute maybe 2, maybe 3, or an arbitrary number of processes in parallel. And then we want something like a model checker that tells us whether a specification holds, regardless of the number of copies that execute the program concurrently. This is what's called the parameterized model checking problem. Now, well, as I showed it before, this is not very interesting if the processes just execute in parallel but do not communicate in any way. So usually we consider systems where we have certain labels on the transitions that allow the processes to communicate. I will give you a few more concrete examples later on, but in general, communication between processes, different forms of communication, will be an important point in this talk. Now, when we're talking about parameterized model checking, the problem has long been known to be undecidable, even in case that we have identical finite state machine that all execute the same program. This problem is not decidable in general. So because of that, there are 2 ways out of that. One is we drop decidability. We go to a semi-decision procedure and have something like in software model checking where we don't know whether it will terminate or not. Or, and that is the point of this talk, we want to have a decision procedure. And then there has been a wealth of different results for different types of systems, mostly distinguished by how processes can communicate. And one of the main points of this talk is that while these systems have certain things in common, usually the results that prove decidability of parameterized model checking use completely different proof techniques. And in our work, we find a unified framework that captures the 4 results essentially that we have here on the screen and a couple of others. Okay, so that sets up my talk. And in the rest of the talk, I will first walk you through a couple of these known results that we capture in our framework. Then I'll introduce on some level of detail our proof techniques, which allows me to state different problem classes and decidability results. And if there's time, I will talk additionally about an efficiently decidable subclass. All right, so the first model that has been studied in the literature before is lossy broadcast, also known as reconfigurable broadcast networks or mobile ad hoc networks. These are all essentially the same thing. What does it mean? Well, if this is our process template, so every process executes this program essentially, then transitions can be labeled with either a sending action A or a receiving action A. And if a process executes the sending action A, then other processes can receive this A message and can react to it by taking a receiving action A. So in this example, we start with 3 processes in this initial state here. This is how we can represent global states, or we can represent them as vectors. Here in this example, 3 processes are in the initial state, 0 processes are in Q1, and 0 processes are in Q2. This is a very common way for representing these global states. And now, if one process takes the sending action on A and moves here, then at the same time, the other processes that are also in the initial state currently can take the receiving action and can move there. Now, I said can because lossy broadcast means the message might actually not arrive at these processes. So another option is that the sender goes here and only one of the receivers goes to Q2. The other one didn't get the message and stays in the initial state. Or even the sender goes to Q1 and none of the potential receivers actually receives the message. So this is how lossy broadcast works. And these systems have been studied. And the first proof that parameterized model checking, certain parameterized model checking problems are decidable was via a reduction to Petri nets. And actually a later proof for safety properties uses something that is very, very similar to our 0-1 abstraction and was actually one of our inspirations. So moving on to another system model that is actually closely related to lossy broadcast, which is systems communicating through disjunctive guards. So here, a transition can be labeled with a guard that in this case here says exists Q2. So I also like to call them existential guards. Actually, I like that better because the semantics of this is if a process, now here again, we start with 3 processes in the initial state. If a process wants to take a transition that is labeled with such an existential guard that says exists Q2, then this is currently not enabled in this global state because the guard says there must exist another process that is currently in Q2 and that is not satisfied here. But the transition from the initial state to Q2 is actually enabled. So another process could move there, and then the transition with exists Q2 would be enabled, and the process could go there. So this is the semantics of disjunctive guards, and systems with disjunctive guards have also been studied, and decidability of parameterized model checking has been proven, but the proof here is completely different from the Petri net or the 0-1 abstraction proof. It's actually by constructing a static cutoff that only depends on the number of states in the system. And so a cutoff means I have a number of processes that I have to compose, and then I know that I can see every possible behavior of the system, essentially. If I add more processes, nothing new will happen. OK, so this was 2 types of systems, disjunctive guards and lossy broadcast. I just want to mention a third one, which is just simple synchronization. You might notice just from synchronization of transition systems. Here we also have labels on the transitions. For example, the label A, and the semantics is that all the processes take an A transition at the same time. So if we start in this initial state, for example, 2 processes move up here, 1 process moves down there. They could take either of them, but they have to take one of the A transitions if an A is fired. Okay, and there's a couple of other systems, for example, asynchronous shared memory systems and immediate observation protocols that are somehow related, and we will see that they all fit into our framework, but that have been until now studied separately, and each of them for each of them its own proof technique has been developed, and that's like the state of the art. If you have a new system model, you always have to come up with your own proof technique and show that parameterized model checking problem is decidable. Okay, so that covers the known results more or less. Now to our technique. So what is the heart of our technique? It's what we call 0-1 counter abstraction, or simply 0-1 abstraction. So in our example for the lossy broadcast, we have seen a possible step for 3 processes in the initial state. But since we're talking about parameterized systems, there could be any number of processes. So what happens if we have 10 processes? We might, after a couple of steps, end up in this configuration. And the size of these configurations is a priori not bounded, so it might be very expensive to reason about these systems. Now, the idea of 0-1 abstraction is that we don't want to count how many processes are in which state. Instead, we just want to keep track of which local states are occupied and which are not occupied. So here, so it's just a black and white 0-1 thing. Here, the initial state is not occupied, but these other 2 states are occupied. And so now to make this a bit more formal, these systems without abstraction can be represented as counter systems. So what I mentioned before, global states can be seen as vectors, which have natural numbers, and the number of positions in the vector is given by the number of local states of our protocol. And the abstraction function that maps this just to zeros and ones takes such a vector and maps it to a vector of Booleans of the same length, where we assign a 1 if there's at least 1 process in that local state, and we assign a 0 if there's none. So in our example, both of these states with 3 or with 10 processes, their abstraction is the same, and it's 0, 1, 1. So this is the abstraction of both of these states. And then based on such an abstraction function alpha, we can define a 0-1 counter system, which is defined in the standard way, an abstract transition system based on such an abstraction function. So our global states are now these Boolean vectors, and there is a transition between 2 abstract states whenever there is a transition between the concrete states in the concrete system. This is like a standard definition of an abstract transition system. And now we're interested in cases where this 0-1 abstraction is precise in the following way. We want to have that a global state given by a vector v is reachable in the original system if and only if its abstraction, alpha of v, is reachable in the abstraction, the 0-1 counter system. Now, in order to identify for which systems 0-1 abstraction is precise, we use tools that are already known in parameterized verification. In particular, we use a well-quasi order. Well-quasi orders are known from well-structured transition systems, where you have a well-quasi order and you have to show that your transition relation is fits the well-quasi order, so to say. I will explain in more detail later on what it means. And there is like a standard well-quasi order that says, well, a global state v is smaller than a global state v prime if and only if for every position of the vector, the number in that position in v is smaller than the number in v prime. So the number of processes in a local state is bigger in v than in v prime for every local state. And we refined that well-quasi order, or an example, or a couple of examples would be here with the standard well-quasi order. 0, 1, 0 is smaller than 0, 42, 0, because every position is smaller. 0, 1, 0 is also smaller than 0, 42, 1. But 1, 0, 0 is not smaller than 0, 42, 1, because in the first position, this first one is bigger than the second one, so it doesn't fit. Okay, so we refined that well-quasi order for our systems. For the 0, 1 abstraction, it turns out that this is an important well-quasi order, where in addition to what was necessary before, we require that the two vectors agree on the positions where we have zeros. So the empty locations where no process is need to be the same. So with the same examples now, 0, 1, 0 is still smaller with respect to our new well-quasi order than 0, 42, 0, because they agree on the positions where they have zeros, and in the other position, 42 is bigger than 1. But the second case doesn't hold anymore, because now we have a 0 in the third place on the left and a 1 in the third place on the right. So these two are not comparable. And the last one is also not comparable like in the first case. In this case, for multiple reasons. We don't agree on the zeros, and we're bigger here than we're here. Okay, so we have this new well-quasi order. And I said this is necessary or helps us to identify when the 0, 1 abstraction is precise. And this brings me to our first result that says, if a counter system, C, so the non-abstracted one, is compatible with this 0, 1 well-quasi order, and in our case, we need it to be forward and backward compatible, then C has precise 0, 1 abstraction, so then we can use the 0, 1 abstraction to check reachability, and it will be precise. We get an if and only if relation. So I didn't explain yet what compatibility means, so let me do that. Compatibility with a well-quasi order means if we have a global state, V, and a transition to a global state V prime, and we have another global state W, which is bigger than V with respect to our well-quasi order, then there must exist a transition to a W prime from this W, such that W prime is again bigger in the well-quasi order. This is forward compatibility because we took a step forward. And backward compatibility is what you would expect. So we start with V and V prime again, and we have something, a W prime that is bigger than V prime. And now we need to be able to go backward. We need to show, or we need to guarantee that there exists a transition from some W to W prime, where W is, again, greater than V in our well-quasi order. So this is compatibility with respect to our well-quasi order now. And we need to prove this for all possible actions in all configurations of the system. And actually, we can prove that for all the types of systems that I talked about so far. So for lossy broadcast, disjunctive guards, synchronization, all of them have steps that are compatible with this well-quasi order. And now, what does it mean? Based on the lemma that I already showed you before, this means, well, if we wanted to do parameterized model checking for such a system, if we want to do it in a naive way, we would construct a counter system which has an infinite state space, so checking reachability might not be decidable. But if we can show that they're compatible with this well-quasi order, we know that the abstraction to the 0, 1 counter system is precise, and then we can check reachability of the abstraction of the state that we're interested in the 0, 1 counter system. And this is, the abstraction is a finite system, so this reachability check is decidable. So that's what we get for all of these systems, just by identifying this relation between the well-quasi order, the 0, 1 well-quasi order, and the 0, 1 abstraction of the transition system. But I said in the beginning, model checking we might be interested in more complex properties, so we can also cover that. An example is coverability of a relation. We just might want to say, well, the number of processes in some state QF that we're interested in should be greater or equal to 1. Can we reach a state where this holds?
Hello, can you hear us?
And we also can have a separate control process, which is essentially supported in the 0-1 abstraction without additional cost, which is not true for all of the existing results for the systems that I showed you before. And then the cardinality reachability problem is for an input C, a counter system, and a cardinality constraint out of this grammar, decide whether C can reach a configuration that satisfies the constraint. And then what we get is our main result if the counter system is compatible with our well-quasi order and a small side condition that it is polynomially abstractable, which essentially means we can get the abstract counter system at polynomial cost from the description of the original system. Then the cardinality reachability problem is decidable and it's in p-space. And the proof is not difficult given what we have already seen. Essentially, since p-space is the same as non-deterministic p-space, we can guess a path in the abstract system, and then we can just check it. Okay, so that's nice. For all systems that are compatible with our well-quasi order and satisfy a small side condition that is also satisfied by all the systems that I showed you, we get decidability of this problem, this more complex problem in p-space. And actually, we can also show that the CRP for this class of systems, even if we restrict it to systems without a controller and with only literals of the form the number of processes in a state should be greater than 1, is already p-space hard. Okay, so it seems I need to speed up a little bit. So this is already a really nice result, I think. It captures a lot of existing models and generalizes the results for these models somewhat, but not too much. But now we can actually go beyond these existing models. So we've seen, for example, lossy broadcast and disjunctive guards or existential guards. We can actually mix them in the same process template, and it will still fall into our fragments. That is one of the easy corollaries that we can get. I already mentioned we can also have a controller process, so only one process will execute this process template, and an arbitrary number will execute this process template. And we can go beyond that. We identified a new communication primitive, which we call guarded synchronization. So we have these synchronization actions that we had before, but now we can actually guard them both with existential and with universal guards. So the idea of the semantics is this B transition can only be taken if there exists another process in Q2, and if all processes are either in Q1, Q2, or C1. So no process can be in one of the initial states or in Q3. And this is kind of surprising because it's known that with individual transitions with guards, this would lead to undecidability, but we can add it to the synchronization steps, and we can even mix it with everything we've seen before, and it will still stay decidable. Okay, so guard synchronization steps are compatible with the well-quasi order, and also mixing these things in one template also works. Okay, so to summarize this part, and actually, yeah, let me just go to the conclusion. So I'll just say one sentence about improving this. So we are inspired by existing results that for some of these models, the problem is decidable with a lower complexity. We also identified a subclass of our systems in which we match the complexity results that we get from this previous work. And it's essentially based on this additional condition. You can look it up in the paper if you're interested. And it holds, for example, for lossy broadcast and disjunctive guards. Okay, so let me wrap up. We looked at the parameterized model checking problem for different types of systems and unified them into a framework that is based on compatibility with the 0-1 well-quasi order. And if we can prove that compatibility, then we can check cardinality constrained reachability in the abstract system in the 0-1 abstraction. And this holds for many known communication primitives, their combinations, and new communication primitives. And even with a controller process, the cardinality reachability problem is decidable in p-space. If you're interested in details, you can find it in the proceedings or in our archive paper. And with that, I'd like to conclude. Thank you very much.
Thank you. Can you hear us?
Yes.
Okay, great. Do we have questions? Yes, we do.
Hi, Swen. This is Kedar. That was a great talk. So I was, yeah, this is a really nice generalization. I guess my question, which is sort of a natural one, is can you go beyond reachability, like to, you know, linear temporal properties, eventuality, that kind of thing? So it seems like, you know, this probably breaks down at some point. Do you have an idea of where it does? Because some of the earlier results you quoted, they also, I think, can handle some amount of linear time properties.
Yeah, this is true. So for the lossy broadcast and for the disjunctive systems, there are also results for Leibniz properties. But we have an example in our paper that for Leibniz properties in general, the 0-1 abstraction does not work. So you would have to invest additional work to get Leibniz properties, to decide Leibniz properties. We have looked at it, but it's work in progress. We don't have results. But I mean, we have other results that build on the idea. So we had a paper in formal methods last year where we use 0-1 abstraction in the context of deciding threshold automata, and we have an archive paper where we use implicitly at least 0-1 abstraction on networks of timed automata that communicate by lossy broadcast or disjunctive guards.
Okay, thank you. Any other questions? All right, so I had a tiny question. Can you comment, is there a relationship between this and finite model property? Because like some of the results you mentioned, decidable by reducing to a finite model, like does that also carry now to other systems, or is that just completely unrelated?
Yeah, I mean, implicitly, I think, well, not implicitly, I think it would allow you to compute a cutoff also. I haven't thought about it, so I'm just making this up, but
I wonder.
I think there is a connection.
So you don't think that there are systems for which there are no finite model property, but the 0-1 abstraction is complete?
Say again?
So you're saying probably there are no systems for which there is no finite model property, but 0-1 abstraction is complete.
there are definitely systems for which 0-1 abstraction is not complete or not precise. But I mean, the other way around, if a system has 0-1 abstraction, then I think you can get a finite model property out of that, yeah.
Okay. I mean, because there are decidable parameterized systems for which there is no finite model property.
Mm-hmm.
Right?
Yeah,
Like you do
that's
something
true.
slightly different, like interference of some kind. Oh. Thank you.
Yeah, definitely. Thank you.
Thank you so much. Sorry that you couldn't be here.
Yeah.